Hi gents, so today's lesson is on Boyle's Law. Let's have a look at the lesson objectives. So after today's lesson, you should be able to understand and explain the relationship between the volume and pressure of a gas. You should be able to recall the quantities that must remain fixed in order for this relationship to hold true. You must be able to recall the formula that enables us to solve problems involving Boyle's Law. And finally, you need to be able to use that formula to solve problems. So in order to understand Boyle's Law, we need to just go back and recap what we know about pressure. So up in the top right hand corner here, I've got a little animation of some gas molecules zooming around inside of a container. Now, every time one of those gas molecules collides with the side of the container, it changes direction. And if it changes direction, it's undergoing a change of momentum. Now, if you think back to the beginning of the course when we talked about momentum, in order for an object's momentum to change, a force must be exerted on it. That's effectively Newton's second law. So we now know that all of those gas molecules that are zooming around inside that container, every time they collide with the side of the container, they're having a force exerted on them. Now think about Newton's third law. If the side of the container is exerting a force on the molecule must be exerting a force on the side of the container. So if we then think about what we know about pressure, pressure is the force per unit area. So we've managed now to explain why a molecule colliding with the side of the container exerts a force on the side of that container, and hence why there is a pressure exerted on the side of that container. So what's going to affect the size of this pressure that is exerted on the side of the container? Well, the first thing is going to be the mass of the gas. If we increase the number of particles, we're going to get more collisions between the molecules and the sides of the container, and therefore we're going to increase the pressure. In fact, these two quantities are proportional. If we double the number of particles, we're going to double the pressure. I tend to use a bit of a stupid analogy here of cats. If you think about a room filled with cats, they're going to go meow randomly. Now, if you double the number of cats in the room, you're going to double the number of meows per second. So the same thing's happening here. If we double the number of particles within our container, we're going to double the number of times we get a collision between a molecule and the side of the container. Hence, we're going to double the pressure. Now look, you don't really need to know about the relationship in terms of the fact that they're proportional, but you do need to know that the mass of the gas inside that container is going to have an effect on the pressure. If we increase the mass, i.e. the number of molecules, we're going to increase the pressure and vice versa. Okay, what else is going to affect it? It's the temperature. If the temperature of the gas is increased, the average speed of the molecules is going to be higher. And this is going to result in two things happening. First of all, the particle is going to collide with the sides of the container more frequently, and hence the pressure is going to increase. Also, when they do collide with the side of the container, there's going to be a bigger change in momentum. They're going to be traveling faster in the first place, and so then when they bounce off, that change in momentum is going to be bigger, and hence the force is going to be bigger. So again, if we increase the temperature, we're going to increase the pressure. Again, we don't need to actually be able to do that mathematically. We don't need to be able to talk about it quantitatively, but you do need to be able to talk about it qualitatively. So you do need to be able to say that as the temperature goes up, the pressure is going to go up, and vice versa. And the final thing that is going to affect the pressure of our gas in our container is the volume of the container itself. If we increase the volume of that container, the number of collisions per second is going to decrease. What I always like to talk about when I've got a room full of students with me is if I got all those students to stand up and walk around the classroom in perfectly straight lines and only change direction when they either collide with each other or with the walls of the container, they're going to collide with the sides of the classroom, the sides of the container, a certain number of times per second. If I then got the same students, the same number of students, traveling at the same speed to do the same exercise in a classroom half the size, they're clearly going to collide with the sides of the container more often, because you're not going to have to travel as far before you get to a wall. And so here we've got a situation whereby increasing the volume decreases the pressure, and obviously vice versa. Now, with mass and temperature, we only need to be able to talk about their effects on pressure qualitatively. So we have to be able to say that as the mass goes up, the pressure goes up. As the temperature goes up, the pressure goes up. But with this aspect, with the volume, we also need to be able to do it quantitatively. So not only do we have to be able to say that as the volume goes up, the pressure comes down, we also need to be able to actually put numbers to it. Now, in order to do that, I'm going to show you a bit of a demonstration. So I'm going to cut to a video now, which shows the piece of equipment we would use to show that relationship. So this is an experiment that I would be showing you if you were in class. It is a piece of equipment that enables us to investigate the relationship between the pressure and the volume of a gas. So what I've got here is a bike pump. I'm going to use that to increase the pressure of the air acting on the top of the fluid in this chamber here. Now, if you think back to what we know about something like a manometer, we know that the pressure on the top of that fluid there must be the same as the pressure on the top here in order for that liquid to be stable. So by measuring the pressure of the air here, which is what this gauge does, we know what the pressure of the air in that side that tube is. On here we've got a scale which enables us to measure the volume of the gas inside that tube. So I've got a little valve on the back here, and so if I undo that, I can release some of that pressure, so I can change the pressure, and that obviously then changes the volume. And so what we can do is we can take various measurements of pressure and volume. Now, I'm not going to sit here and actually do that because it's not going to be particularly very interesting for you. So what we'll do is we'll cut away to a set of data that I have collected using this piece of apparatus, and we can then have a look at the relationship between those two quantities. So I've now taken the data from that piece of equipment and I put it into this table here. So we can see here that as the pressure decreased, so as I released that valve and let more and more pressure out, that volume was increasing. Now, I want you to look at that data. I've added a third column here, but look at that data and can you spot any kind of relationship between them that is going to be relevant? I'll give you a couple of seconds before we move on to the next slide, but just think about kind of what kind of connection you can see between those values. Okay, so what I've done here is I've added in a header for that third column, and it's P times V. I'm hoping some of you realised that if we multiply these values together, we are going to get this roughly the same value. So let's go through and look at that. 350 multiplied by 20 is going to give us 7,000. 300 multiplied by 23 is going to give us 6,900. 250 by 28, 7,000, and so on. Now we can see that all of those values are pretty much the same. We're always going to get a little bit of kind of deviation just due to the fact that it is a real practical. We're never going to get perfect values every single time. But I think we're confident enough with this experiment to be able to say that the pressure times the volume is equal to a constant. Like I say, we do have a slight bit of deviation, but that's all within acceptable experimental tolerances. So to summarize, PV is always going to be a constant. So how is this statement going to help us? Well, if PV is a constant, let's do a little bit of maths with this. I'm going to call that constant K. So I've got here that PV is equal to K. And I'm going to rearrange this. So I'm going to divide by V, and I'm going to get P is equal to K over V. Now I'm going to ask you to think about some of the maths you've done in terms of proportionality. I don't want this equal sign here. I want to talk about something in being proportional. And I'm hoping that you've done enough maths at this point to be able to jump from this stage to this stage, to say that the pressure is inversely proportional to the volume. So this is a really important statement. This one here, that pressure is inversely proportional to volume. And so this is what Boyle said. This is Boyle's law, that for a fixed mass of gas at a constant temperature, the volume is inversely proportional to the pressure. Now that's a really important statement. We must be able to remember it. We often get asked questions in the IGCSE where we're actually asked to state what Boyle's law is, and it is really important that we add those two bold underlined statements that it is only for a fixed mass of gas and only for a constant temperature. But if those two things are held constant, if they are fixed, then we are comfortable in saying that the volume is inversely proportional to the pressure. Okay, so again, I want to look at this in a little bit more detail. So I've got P times V is equal to constant. Now, let's look at an example involving a cylinder. So I've got a cylinder here on the left-hand side. I'm going to call this situation 1. Now, in situation 1, I've got a pressure of P1 and I've got a volume of V1. So I'm just using the subscript 1 there to effectively denote situation 1. And we know that P1 times V1 is going to be equal to some constant. Now let's have a look at that piston when it's been pushed down. So we've got the piston head has come down, it's squeezed that gas a little bit. So I'm going to call this situation 2. Now in situation 2, I've got a pressure of P2 and I've got a volume of V2. And we know that P2 times V2 is also equal to a constant. Now, provided that the mass has not changed, so no gas has either entered or left that cylinder, and provided the temperature has stayed the same, and I might talk about that in a little bit more detail in a second, but provided those two things are fixed, we now know that P1 times V1 is equal to P2 times V2. If they're both equal to the same constant, they must be equal to each other. Now, this statement is very important. This is a really important formula that I want you to remember. So I want you to take the next couple of days, just remember, get that in your head. Boyle's law in its kind of formula version is P1V1 is equal to P2V2. Now, I just want to go back and talk about that temperature situation again. In reality, if you compress some air in this way, it is going to heat up. You probably know this. If you've ever kind of put your finger over the end of a bike pump and tried to pump it up, you'll feel the temperature increasing. You certainly would have felt it in the opposite direction. So when you go from high pressure to low pressure, so something, say for example, like an aerosol can, you wake up in the morning, you put some deodorant on, that aerosol, that deodorant is very cold. Well, that's weird because it's at exactly the same temperature as the rest of your room because it's been in your room for the whole day. So why is it cold? Well, it's because of the fact that that gas that's coming out of the cylinder is going from a high pressure to a low pressure. And when that happens, it decreases its temperature. And the same is the opposite. It's the same the opposite way around. So if something goes from a low pressure to a high pressure, its temperature increases. But that temperature change, although it's going to happen, is probably going to be relatively small, and in most cases, it's going to kind of return back to its original temperature in the first place. So, I mean, it is a simplification. So when we do the questions that we are going to be asking or answering, we're going to have to assume that the temperature stays the same. In reality, will it? Probably not, but is it going to have a massive impact on our answer? No. So we are going to assume in nearly all the questions that we answer for Boyle's law that temperature remains constant. Okay, so I've got a couple of worked examples I want to go through with you so that you are able to then answer your own questions in the next lesson. So the first one here, a student conducts an experiment to see how the pressure of a gas varies with its volume. Here is the data he collected. So we've got the volume and the pressure. So it's effectively the same experiment that I showed you earlier on. And the question is, does this data support the idea that V is inversely proportional to P? So is the volume inversely proportional to pressure? Well, let's have a look about how we're going to answer this. So here's our data. How are we going to do it? Well, if these two things are proportional, if we multiply them by each other, they should give us the same value. They should be a constant. We've said that P times V is a constant. So let's have a look at it and see if it works with this set of data. So that top row, 20 times 4.5, is going to give us 90 kilopascals centimeter cubed. Let's do it for the next one. So 30 times 3.0 is going to be 90 kilopascals centimeter cubed. And let's do a third one just to make sure. Got 92. Again, we've got to expect some kind of deviation just because of the fact that it's an experiment, it's a real life problem. We're going to get some kind of variance, but I would say that is definitely within an acceptable experimental tolerance. And so I would say, yes, these things definitely are proportional. We know that because when we multiply the two together, they always give us the same value. Okay, the next question. We've got here a gas inside a cylinder of volume 0.0015 meters cubed that has a pressure of 180 kilopascals. If I was in an exam, I would possibly be circling these values just so that or underlining them, highlighting whatever, just so that I know, what I'm dealing with. It says the piston head is then pushed down, resulting in the volume decreasing to 0.0011 meters cubed. Now, instantly, I should be thinking, right, if the volume's going down, the pressure is going to go up. And I can use that at the end as a check. But we need to actually we need to be able to look at this quantitatively. So we actually need to be able to calculate an answer. Let's look at the next slide of how we're going to do that. Okay, whenever I get a question like this, I think it's really important that we start by drawing a diagram, and it helps us just kind of like bring all our ideas together, or all our kind of information together in a really visual way, and it just helps us kind of tackle the problem. So let's have a look at what we've got. We've got two situations. Situation one is our piston when it's up the top of the cylinder. So I've got a volume of 0.0015 meters cubed and a pressure of 180 kilopascals. In situation two, I've got the piston head has been pushed down and I've got a volume of 0.0011 meters cubed, and the pressure I don't know. That's what I'm trying to find out. So how are we going to solve this? Well, we're going to have to use that equation that we saw earlier on. P1V1 is equal to P2V2. And now all I need to do is go ahead and substitute my values in here. Now, something that's worth noting here is the units are irrelevant. It doesn't matter what units we use because we're going to have the same unit on both sides of the equation, so they're just going to cancel out. So even if the pressure was given to you in millimeters of mercury or a unit of, I don't know, Smiths, it'd be completely irrelevant. Just go ahead and plug those values in. Just make sure you've got the same unit on both sides of the equation. So I'm just going to stick with what I've got here. So I'm going to put in here that the P pressure for situation one is 180, and the pressure for the volume for situation one is 0.0015. I don't need to worry about the kilopascals because, like I say, I'm going to put kilopascals on both sides and they just cancel each other out. So on the right hand side here, I've got P2, that's what I don't know, and I've got 0.0011 meters cubed. So I now need to rearrange this equation. Now, depending on your level of maths ability, you might actually just want to work out what this value is here on your calculator, and that just reduces your formula down to a 3-term equation. But I'm going to stick with 4 terms. If I want to get this P2 on its own, I want to get this term here on its own, what do I need to do? Well, I need to get rid of this times 0.0011. How do I get rid of a times 0.0011? I divide by 0.0011. So I'm going to get P2 is equal to 180 times 0.0015 divided by 0.0011. And that comes out to be 245.45. Now, obviously, everything in my question is given to 2 sig fig, so I need to round this to 2 sig fig as well, and that then comes out to be 250 kilopascals. Why is it kilopascals? Because I put the pressure up here into my equation in kilopascals, so this value is going to come out in kilopascals also. Okay, the second part of that question was, what have you assumed in answering this question? Well, we need to think back to the two things that needed to be fixed, and they are the mass of the gas and the temperature of that gas. So in order for P times V to be a constant, those two quantities must be held constant. They have to be the same. So that's what we have assumed in answering this question. Okay, the third and final worked example, the gas inside a rigid cylinder of volume 220 centimeters cubed and pressure 190 kilopascals springs a leak. If the atmospheric pressure is 101 kilopascals, calculate the volume of gas that escapes. Again, the first thing I'm going to do is I'm going to draw myself a diagram. So here's my diagram. I've got all the information that I need on here. Again, I've got a situation 1 on the left and I've got a situation 2 on the right. With situation 2, I've actually got some gas still in the cylinder and I've got some gas outside the cylinder, and I've just drawn a dashed line around that to show that that's kind of the gas that has escaped. So let's go back to our formula of P1V1 is equal to P2V2, which is what I've got here, and let's plug in some values. So the P1 and V1 is very straightforward. That's going to be 220 multiplied by 190. Again, don't worry about the fact that it's in centimeters cubed rather than meters cubed. As long as I put it in on both sides, I know I'm going to be good. And on the right hand side, I don't know what the final volume is going to be, but I do know the final pressure is going to be 101, because when this cylinder springs a leak, it's going to continue to expel gas until the pressure inside and the pressure outside is the same. So the final pressure is going to be 101 kilopascals. So I've got 190 times 220 is equal to 101 times V2. And so that's going to give me a final volume of gas of 414 centimeters cubed. Now let's have a look at this on the right hand side. So what we're saying is I've still got some gas inside that cylinder, and that's still got a volume of 220 centimeters cubed. And the rest of my gas is out here. We're going to say here that the total volume is equal to the volume in the cylinder plus the volume outside. Well, we've just worked out what the total volume is. It's 414. We know the volume in the cylinder, it's 220. The only thing we don't know is the volume outside. So we're going to get 414 is equal to 220 plus our final answer, the volume that is our final answer. So if we rearrange that, we're going to get our final volume to be 194 centimeters cubed. So we've got 220 still in the cylinder, but 194 outside the cylinder. And so that is our final answer there, 194 centimeters cubed. So if you haven't been making notes whilst you've been watching this video, please go back and do that. It's really important that you've got something to use for your revision next year. So all of the statements and diagrams that I've drawn I want to see in your notes, with certainly all the worked examples at the end. And then in next lesson I'm going to send you a worksheet that's just got lots of questions on Boyle's Law, which you can then complete and submit following the instructions that are going to be on Show My Homework next week. Good luck.